Hello, my name is Peter Robak and I come from the Elmer team at CSC. This presentation is about the Elmer SIF file, which is the shortening for ElmerSolver Input File. So I'll explain about the content of the file and give some instructions how to write it. The basic structure of the SIF file is as follows. We have sections and we have keywords. Each section starts with a section name and ends with end. There is also a shorter alternative form if there is just one keyword in a section. In each section we may have any number of keywords. Keywords can be of 5 different types. These are real, integer, logical, string and file. The difference between string and file is that string is not case sensitive, whereas file is case sensitive. The sections are header, constants, simulation. These 3 sections can only have one instance, whereas the sections solver, body, equation, body force, material, initial condition, boundary condition can have one or several instances. So you should always give the number even if it's 1. There are also 2 other sections that are not so frequently used, called run, control and component. So not all sections are needed. You typically have most of them, but not necessarily all of them. For instance, initial condition is rarely used if we have a steady state case. Here is a minimal example of a SIF file. So the take-home message here is the style, how it's written out. So we have sections, and within each section we have tabulated keywords and their values. So it's a good idea to put some additional space before each keyword, so we get this nice structure which is easy for the human eye to perceive. Here are some further details of the SIF file. You can use comments. They start with an exclamation mark. Avoid non-printable characters. So for instance, if you want to have some indentation, use rather spaces than tabulators. Don't rather use special characters from your native language, but stick with the more limited character set of the English language. Many keywords, they are defined in the Solver keywords database. Unfortunately, many are not. So in case of those keywords, you must give the type. So it can be real, integer, etc. Keywords can also be of other size than 1. So for instance, integers and reals, they can be arrays. And in that case, you should give the size of the array. The unit system is on the user's responsibility, so you would of course want to have a consistent unit system. Elmer does not provide any tools for checking that, so you must do it yourself. Usually we use SI units, but for special application fields also other unit systems are often used. The order of sections is mainly arbitrary. So for the exception of header, you can have the sections in any order. People have different preferences in how to group the different sections. So you can order them according to your own taste. However, the sections with indexing should start from number 1 and the numbering should be continuous. You can use include statements. Those are handy if you want to improve the modularity of the SIF file and maybe do some scripting, etc. So include, for instance, material.sif here would be used to include the material parameters in a SIF file. You have 2 different scripting languages, MATC that comes with the Elmer, and Lua, which is an external library, and both can be used. Lua is quite a bit faster, and is therefore currently recommended. Both can be used in pre-processing mode and runtime mode. So if they are used in this pre-processing mode, then these constants are evaluated once when the SIF file is interpreted. But if you see this MATC or Lua expression, then these are evaluated or every time in the code that these expressions are needed. The difference for the preprocessor directive is that MATC uses $, whereas Lua uses crisscross. The real valued keywords in Elmer can depend on field values. This is actually the main way in which weak coupling between different solvers is often implemented. So we have material parameters that depend on the field values of the other solver. So the simple tabular dependency is the maybe most straightforward to use. So you can define control points and values at the control points. So for instance, here we have defined temperature on different points and give the corresponding density. And between these points we use interpolation, and outside we use extrapolation. And the interpolation can be done using linear interpolation or cubic spline interpolation. We can also use both of the scripting languages, so MATC or Lua. The scripting languages take one or several field values, and the field value is casted to the tx variable. So always, for instance, here the temperature becomes tx. If we have more variables, then the tx may become a vector, but always it is a tx. And the first component here of the tx in C syntax is tx0, and it now of course refers to the temperature. So the two expressions are the same. The difference between MATC and Lua is that MATC uses ordinary parentheses, whereas Lua uses square brackets. The fourth option is to use user-defined function. So for instance, here we use a procedure myproc, which is to be found in my module, and the example for the my module is given here. So we have a simple subroutine which has a constant API. This API should always be used for the user-defined subroutine. Here the temperature is now the T, and N is the nodal index, and model is basically the whole Elmer model, including all the data in the structure. So here we evaluate exactly the same function and return the value as the return value of the function. This procedure can easily be compiled. Every successful Elmer compilation comes with compilation script Elmer F90, and we can compile a shared object in Linux or DLLs in Windows easily using this script. As said, keywords can also be vectors and tensors. So here, for instance, we have defined a heat conductivity that is a 3×3 tensor. This could be used for anisotropic heat conductivity. This is a gravity vector. The first three components define the direction, and the fourth one defines the amplitude. And here we have some integer values. For instance, we could define which nodes to save the results in. Here we go through the sections of the SIF file one by one and explain what each section includes. So the header section should always be the first one. It includes information how to treat the keywords. Should we warn if a new keyword is found, or should we abort, or should we echo everything? It should also include mesh database. So here, for instance, we expect to find the mesh in directory mymesh. Also, it can include path for checking the shared objects, or a results directory for saving results, but these are not mandatory. The simulation section includes stuff that is global for the whole simulation, so it is not, for instance, solver specific, but is valid for the whole simulation. For instance, we defined the maximum output level, which defines the verbosity of the simulation. We can define the coordinate system. We can define what kind of time dependency model we have. Is it transient, is it steady state, or is it scanning mode? If it's transient, we can define the time stepping strategy, what time stepping method to use, what is the length of the time step, how many time step intervals do we take, etc. We can define how often we save the results. If it's a coupled system, we can define how many steady state iterations we take, and so on. And finally, we can also define where the results will be saved to. So if the suffix is VTU, then we know that this file can be read by ParaView after it has been saved to the file system. Constants section, surprise, surprise, includes definition of some constants. Here, for instance, we have defined gas constant and Stefan Boltzmann constant. A body is a leading dimensional part of the mesh. So, for instance, in 3D, this would be a 3D part of the mesh. The mesh can consist of one or several bodies. And the body section basically just tells what equation, what body force, what initial conditions, what materials to include in this body. Equation section basically says what solvers do we want to solve in this equation. And because equation is related to certain body, this means that we can define in the equation what solvers are valid in each body. Equation can also include some other keywords. For instance, here we have defined the keyword convection, which is read by the heat solver to define how we want to, or whether we want to apply the computed convection in advecting the temperature field. The solver section includes stuff that is specific to each and every solver. So we have typically the name of the module where the solver lies in, the name of the variable that we want to solve for, maybe some stabilization techniques or other numerical techniques. We can have steady state convergence tolerances, steady state other keywords, or nonlinear system keywords. Here we assume that the system is linear and therefore only have one nonlinear system iteration and no tolerances. And then we have lots of linear system options. For instance, here we have defined that we use a BCG stub method with incomplete LU preconditioning, and at maximum take 1000 iterations. So this can include a lot of numerical techniques and features. So it can be rather short, but also quite long. So I won't go into every detail here. The material section includes the material parameters. Surprise, surprise. So what material parameters are needed. This can be found in the models manual. So if you have a new physical module, you should check what material parameters it needs. For instance, here we would have some material parameters for the heat solver, heat conductivity, heat capacity, and then we have some material parameters for the Navier-Stokes solver, the viscosity model, and here we have some power law model, which then requires some additional parameters. But this is highly dependent on each solver. Initial conditions section basically for transient system includes the initial values. For steady state system, it includes the initial guesses for doing the simulation. So only for linear systems the initial guess might be, let's say, not needed, but even then it might improve the convergence of the linear systems. A body force section would typically be something on the right-hand side of the partial differential equation. So for instance, for heat equation, it could be the heat source. For Navier-Stokes equation, it can be the body force. And for instance, for static current conduction, it could be the current density, etc. We can also have discrete loads that are directly associated to the nodes. So basically, body force comes to the right-hand side of the equation. The boundary condition, as the name applies, it's given on a lower dimensional entity of the mesh. So in boundaries, we can define in which boundaries the boundary condition is given this target boundaries keyword. The keywords can be associated to Dirichlet conditions. So typically we have a name for the variable to be solved, and by defining the name here, like temperature to be some value, we set the Dirichlet condition. But there are also a number of other types of boundary conditions that are typically solver specific. So for instance, we could define heat flux for heat solver, etc. We can define a boundary also to be a body. This means that we could then, using this syntax, we could create an additional body, and in that body solve then some partial differential equation. So partial differential equations are solved on the bodies. So if we want a boundary to have a partial differential equation, then we should declare it also as a body. So this should be the first free number for the bodies. The boundaries can be periodic, they can be mortar boundaries, etc. So we can then have some additional keywords here. Run control is rather new section. Basically, it was written to be able to make parametric scans for transient systems, because when we had this old scanning type of time dependency model, we used the scanning as a pseudo time, and then of course we cannot make scanning over transient systems. So this makes it possible to do optimization also of transient systems, for instance. Also rather rarely used section is the component section. This is something that has been developed for the usages of electromagnetics. So for instance, we could have some magnetic force being computed on some bodies or capacitance, etc. So this is something that you might not often see in real life. Some remarks about the SIF file. When you study the SIF file, and if you look at the code, you will quite quickly realize that there is almost one-to-one mapping between the model type in the ElmerSolver code and the content of the SIF file. So each keyword is basically an entry in the list structure of the model type. So for instance, here we have a list model constants, and in there we are trying to find gas constant, and we use this list_get_constreal function to fetch the value of the gas constant from that list. So if you read the code, you can see that most keywords are fetched in this way, and if you create keywords of your own, it's as easy to obtain their values from the SIF file. Don't be afraid to add new atomic solvers in your SIF file. So for many tasks in Elmer, there exists a separate atomic solver that has one specific task. And so if you want to have a lot of different tasks carried out in your simulation, you must also add many atomic solvers to your SIF file. So you have tens of modules, basically the standard Elmer modules, but also Elmer ICE includes tens of different modules to carry out different tasks. Copy-paste is often a good way to start. So if you find a consistency test, for instance, or a previous test case or previous example that is close to what you need, it's never a bad idea to take that SIF file and use it as a starting point for your own simulation. Just maybe modify something, add some boundary conditions or body definitions, etc. The Elmer's models manual and the ElmerSolver manual have a keyword index. So if you don't know what keywords mean, then you can check those hopefully in the keyword index. And also if you don't know what keywords you need, so these are good places to check what, for instance, what keyword a specific module needs. Unfortunately, documentation is never complete. So if you are don't know something, then go ahead and ask. We try to answer to our best ability. Thank you.